Let's start with this small grammar, which is our running example. The fact that a sentence is composed of noun phrase and verb phrase, and the meaning of the arrow, okay, left symbol going to one or more right symbols indicates that left-hand side phrase is composed of the sub-phrases on the right-hand side. So this says that a sentence is composed of noun phrase and verb phrase, and the noun phrase is composed of determiner and noun or a single noun. And then verb phrase is composed of verb and adverb or a single verb. So you can see that since this grammar is insisting that a sentence begins with a noun phrase, it clearly does not accommodate the phenomenon of questions. Okay, questions and imperatives, which are orders, requests, and so on. So anything that begins with verb, okay, this grammar doesn't accommodate. So this is really a very, very simple segment of the grammar and captures very little of English language. But still, this is good for illustrating our algorithms. Now, we have seen top-down and bottom-up parsing. This particular method of parsing combines the merits of both top-down and bottom-up. Recall that in top-down parsing, the main problem is that if there is any left recursion, then the top-down parsing will get into infinite loop. Okay, the top-down parser will call the resolution of symbols again and again, okay, because it's a recursion. So you have to remove left recursion. The other problem is that in top-down parsing, the methodology is predictive. So we predict that a particular language construct will appear on the input strings, and this may go completely wrong. So useless rules may be brought to the stack, and that can lead to unnecessary computation. The problem with bottom-up parsing is that it can bring useless parts of speech, okay, or useless grammatical constructs on the right-hand side of rules onto the processing frame. Okay, so these are the two disadvantages. So if we combine both these approaches, then maybe we'll have a strategy where both these disadvantages are eliminated. So indeed, there exists such an algorithm, which is also very elegant. And the algorithm goes as follows. We have our running example of people laugh. People can be both noun and verb. Okay, and the grammatical rule is S goes to NP VP. Now here comes in the top-down procedure. So, by the way, all these are rule-based computation. So S goes to NP VP, and there is this dot sitting before NP. Sitting before NP means that we have to finish the word phrase. A noun phrase will have to be found in the input string, input sentence, and then the dot will move over noun phrase and sit before a verb phrase, saying that now a verb phrase has to be found in the input. Okay, so this is the meaning of dot. The dot plays a very important role in the computation of the parsing. So since anyway a noun phrase has to be found, okay, since a noun phrase has to be found, a noun phrase can be found out only in two ways. Either it is a combination of determiner and noun, or it is a single noun. Okay, so we make the dot sit in front of dt and n, and also dot in front of n. So this says that now to find out the noun phrase, either complete the work of finding a determiner or find a single noun. Okay, that's all. So now at this point of time, what will happen is that the word people from the input string will get exposed. Now the bottom-up processing will kick in. So what will happen is that people can be both noun and verb. Since we have to find a determiner or a noun, but not a verb, the part of speech, the verb part of speech of people will not come into the frame. Okay, so you recall in bottom-up parsing, we have to bring all the parts of speech of the words. Okay, so since people can be both noun and verb, we could have brought both verb and noun onto the frame, but not so now. because the expectation is to find the noun. Determinant anyway will not be people is not a determinant. So people has been resolved and we have found a noun, and then the dot moves over NP. That means the work of finding NP is over. So if the work of finding NP is over, then the dot sits in front of VP. And VP's work needs to be done now. We have to find out verb phrase now. So the verb phrase can be found only in two ways, through a verb and adverb or a single verb. So then you can see that this V, ADV, and V coming onto the frame is a top-down process. Okay, the bottom-up process was when people gave N gave NP, and NP's work was over. And since now VP's work has to be done, V, ADV, and V, those words are now brought to the frame. Okay, whether this frame is called chart, is this chart parsing. So finding, so this exposition of V, ADV, or V, this itself is a top-down process. Okay, so top-down first, then bottom-up, then again top-down. This is what is happening. Then we see laugh. Laugh can be both verb and noun. But since we expect verb, we do not bring noun. Okay, from the dictionary. And now verb has been found. So the VP's work is over. So the dot moves over VP. So S, NP, VP, the dot goes over VP. That finishes the work of finding S. So the parsing has succeeded. Okay, so this is a popular algorithm before CYK parsing came, and this is a rule-based algorithm. So this is called top-down, bottom-up parsing. What is the problem that this algorithm will face? What problem will this face? It is still left recursion. You see, because you are expecting the work of NP to be over, so you have brought NP proactively onto the chart. And once the rule of NP comes in, another NP gets exposed. Suppose that rule is recursive, NP goes to NP-PP. So this will go on infinitely. It will not go to the next stage at all. The left recursion problem still remains. So anywhere you have the top-down processing involved, left recursion needs to be eliminated. So this is the algorithm, a rule-based algorithm. Any question on the parsing algorithm? Okay. So similarly, you can take a sentence of any length. If the grammar can accommodate all the language phenomena, then the sentence will be correctly parsed. So the correctness of the algorithm and proper working of the algorithm depends on the grammar and application of these grammatical rules. Okay. Then we had looked at the CYK parsing algorithm. Let me very quickly go over this once again. The importance of CYK algorithm is that in all three generations of natural language processing, CYK algorithm has been used in all three generations. Okay. What are the three generations of NLP? Rule-based, statistical, neural. Okay. The CYK algorithm has remained. So this is an algorithm. And now you should get trained on reading grammar rules. And you should also be skillful in producing grammar rules given a language phenomenon. Okay. So what is this grammar rule saying? This grammar rule is saying that sentence consists of noun phrase, verb phrase. No problem about that. Noun phrase consists of determiner and noun. Noun phrase can also consist of NNS, which is plural noun. Noun phrase can consist of NP and PP. Noun phrase followed by a preposition phrase. Preposition phrase is P and P, preposition followed by noun phrase. VP can be a verb phrase followed by a preposition phrase. Verb phrase also can be VBD, a past tense verb, and noun phrase. Okay, this is a segment of English language. Of course, it doesn't take care of questions and imperatives. Then these rules are called structural rules, not syntactic rules. There are lexical rules, which are DT going to the, NN going to gunman, NN going to building, VBD going to sprayed, and NS going to bullets. So our lexical rules are very few. The dictionary consists of only 5 words. Okay. Now, given lexical rules are nothing but part of speech tags. Given lexical rules and syntax rules, you should be able to see for yourself which strings are grammatical, which sentences are grammatical, and which are not. Okay. So, for example, in this sentence, given this grammar, do you think a man with a binocular in the bus, will it be correctly parsed? Will the grammar admit this? This sentence has 2 preposition phrases. A man with a binocular in the bus. Will it be correctly parsed? So first of all, you will have to apply NP-PP. Okay. Now this NP, we should take care of a man. This will be fine because you have the rule DTNN, but DT is not going to A. If DT goes to A, then a man will be admitted. What about with a binocular in the bus? Will that be admitted? Processed? So PP will be applied. So PP will be applied. PP is P and P. So with will be absorbed. Then we have an NP with a binocular. A binocular will be processed through NP. And again, another PP will be, resolved. In the bus also will be accommodated. Right? A man with a binocular in the bus, and you can have any number of preposition phrases after this. So this grammar is powerful to accommodate that those kind of constructs. With because of P and P. No. With a binocular, with is preposition phrase. P and P. PP goes to P and P. Let's say we have already this is NP. This is P with another NP. Okay, and this whole thing is a PP. And now the binocular in the bus, this will be processed. S goes NPVP. Why we have it? We have it here. Yeah. So I'm processing only the NP part. The man is NP. The rest of it is PP. If I had said, I think so. What you're saying is that you give a VP. The man with the binocular in the bus laughed. Then VP will be resolved. Oh, I'm sorry. I was discussing the processing of NP. Okay. So this is a skill which you have to acquire. Producing grammar and Okay, so the processing, you remember, it's very elegant. So this is essentially a bottom-up parsing. Now, the rows are starting from 0, going up to last index -1. And columns are starting from 1, going up to the last index. Okay? So any cell, ij, corresponds to the segment of the sentence between the positions I and j. Okay, and the indices are between words. Remember that. You may read papers or you may read the textbook material where the indices are word indices. But in this case, the indices are between words, and I personally find these between word indices are much more helpful to discuss the algorithm and the concept. So the processing is fine. It first I see a DT between 0 and 1, which is fine. Then NN between 1 and 2, gunmen, fine. The moment I see this, I'll think of combining the two grammatical entities to form a bigger grammatical entity. So DT NN, there was a rule. This gives the noun phrase. So indeed so. So between 0 and 2, the gunman, which is the noun phrase. Then I find the VVD between 2 and 3. Then I try to see if I can combine VVD with earlier constructs to form a big phrase. I cannot, because I do not have any grammatical rule which ends with VVD. None of them. Then I find a DT between 3 and 4, I find an NN between 4 and 5, building. And I'm able to combine DT and NN between 3 and 5, the building, and get an NP. What about 2 and 5? Between 2 and 5, sprayed the building. Yes, I can combine them and get a word phrase VP. Now, do I get any construct between 1 and 5? Gunmen sprayed the building. No, because I do not have any grammatical rule which says that a phrase can begin with a noun. A phrase can begin with NNS, plural noun. Singular noun, no. And then I'm able to find an S between 0 and 5. The gunmen sprayed the building, which is fine. It's a correct sentence. But the parsing will not stop because the input elements are not yet over. So I get a preposition between 5 and 6, which is P. And I cannot get any bigger construct ending in P because there is no grammatical rule where the right-hand side ends in P. So you see, the bigger grammatical constructs come vertically on the column. Okay, we try to find the bigger constructs vertically on the up on the column. Then I find an NNS bullets between 6 and 7. NNS is resolved as NP. P and NP gives rise to PP between 5 and 7. With bullets is a PP. That's fine. And then I do not find anything between 4 and 7. Building with bullets, no. Singular noun cannot start a phrase. But I can find a noun phrase between 3 and 7. The building with bullets. Then I do not find anything between 1 and 7, but I find S between 0 and 7. Okay. So this completes the parse. And from the table, I can construct the parse tree way. So between 0 and I have S, I have an NP between 0 and 2. Between 0 and 1, I have a DT. Between 1 and 2, I have a noun. The gunman is resolved. Between 2 and 7, there is a verb phrase. This starts with VVD between 2 and 3. And the VVD is resolved with sprayed between 2 and 3. VP has an NPPP. So there is a noun phrase between 3 and 5, the building. And between 3 and 5, I have the and building at two different positions, 3 to 5 and 3 to 4 and 4 to 5. PP is between 5 and 7. Okay. The building between 5 and 7 with bullets. Okay. So in this case, the PP is attached to what? PP, the preposition phrase, is attached to what? Who has the bullets? The building or the gunman? From the syntax, not from the meaning. From the structure, can you answer this question? The building, is it? Why so? Let's find out the path length from building to PP. 1, 2, 3, 4, 4 arcs. And from sprayed to PP, 1, 2, 3, 3 arcs. So it is attached to spray. If it is attached to spray, that means the gunman has the bullets. What is the other parse tree? Other parse tree is this. VP goes to VBD. Now the NP fully captures the building with bullets. The NP between 3 and 7 captures the building with bullets totally. And here the PP is attached to building and not to spray. You can again measure the path length and see. So both the trees are possible, though semantically this is more viable. So gunman has the bullet, right? So gunman and bullet has a very strong association. In today's NLP, that is deep learning based NLP, this strong association is captured by self-attention. Okay, bullets go with gunmen. Okay, now let's do a bit of machine learning. Look at this structure. Machine learning is concerned with primarily classification. Now, look at the first step between 0 and 1. Is there a grammatical construct? This is the question being asked. So is there a grammatical construct? Answering yes or no, that's a decision problem. That's a decision problem. And how the answer is yes. The answer is yes, and it is DT. So how did we arrive at yes? Because the matched the grammatical category DT. So what is the decision rule? If the word matches the grammatical category, put the grammatical category. The answer is yes, and put the grammatical category. Next, the gunman gets NN. The answer is again yes. Now, DT and NN get combined together to produce NP. Again, are we solving the problem? Yes. Can I combine two adjacent structures to form a bigger structure? The answer is yes. Why so? Again, matching. DT and NN match the right-hand side of a grammar rule. And the left-hand side of the grammar rule is placed there. So at every step, we are answering a decision question, or we are solving a classification problem. Okay, so this is the bridge between parsing and machine learning. Choose any classifier and answer these questions at every step of the algorithm. Okay, so let's proceed and enter. Since we have mentioned machine learning, let's take up probabilistic parsing. Okay, which is data-driven or machine learning-based parsing. Any probabilistic NLP ultimately boils down to an argmax computation. So this is a noisy channel modeling. We have we are familiar with noisy channel modeling because part of speech tagging was done by noisy channel modeling. We had an argmax computation there. So T star equal to argmax probability of T given S. Recall part of speech tagging. There T was sequence of part of speech. and S was replaced with W. W is the sequence of words. So we again apply Bayes' theorem, trying to use generative modeling. So PT given S is written as PT into PS given T. Denominator is PS, but that is ignored because the argmax is over T. So now something very interesting happens, unlike part of speech tagging. Probability of S given T is 1. Given the parse tree, the sentence is unique because the lower level, the terminal symbols in the parse tree are the words of the sentence. So given a sentence, you can have multiple parse trees. Given a parse tree, you cannot have multiple sentences. One parse tree, one sentence. One sentence, one parse tree, not true. Okay, so this shows why deeper processing is important. Okay, as we go deeper in the structure, we encounter less and less ambiguity. So finally, when we have the complete meaning graph, there is no ambiguity at all. So this is interesting. Intuitively, the parse tree given the sentence is that tree whose probability is maximum. That is the meaning of this equation. So answer or produce that parse tree which has the maximum probability intuitively, because these are scoring functions. Now the question is, what is the meaning of probability of a tree? Okay, so you have seen the probability of a parse tag, pause tag sequence, and probability of the word sequence given the pause tag sequence. The probability of a pause tag sequence, how did you find it? Probability of pause tag sequence. You've done the assignment. Day after tomorrow is the evaluation. No. The probability of whole sequence. Or in other words, the product of transition probability. Okay, product of transition probability. So probability of a parse tree, what will that be? The probability of big entity is always compositional. You will have to take smaller probabilities and operate on them. What is the operator? Is it plus, minus, multiplication? What is it? That we will find out. Okay, just reflect on this question for 2 minutes. Since you have already done the part of speech tag assignment, and you know how to compute the probability of a whole sequence of pause tag, which is nothing but product of transition probabilities. What could this be? Probability of a parse tree. Very good. Okay. Okay, fine. Good. Anything more specific? What will be the units whose probability will be able to have very easily, and maybe take multiplication of those smaller entities? Okay, so here steps in linguistics. Without that linguistic insight, this particular probability cannot be computed. We will see another such help from linguistics when we discuss word embeddings or vectors. So the language science will now help me. This is data science, probability of T, because the probability will have to be obtained from data. Now language science will step in this way. There is a phenomenon called domination, okay, which comes from language. Domination also comes from sociology, political science, even natural sciences. The notion of domination. Okay, so let me just read this part first of all. A sentence is dominated by the symbol S through the domination of segments by phrases. Analogy, the capital of a country dominates the whole country. The capital of a state dominates the whole state. The district headquarters dominate the districts. So indirectly, the capital of the country dominates all the district headquarters. There is a hierarchy involved. So we say that the S symbol dominates the whole sentence. I saw a boy with a telescope is dominated by the symbol S. We'll make the notion of domination mathematical very soon. Then I say that NP, one NP dominates I. A VP dominates saw a boy with a telescope. A V dominates saw. NP dominates a boy. VP dominates with a telescope. And NP dominates a telescope. DET dominates A. N dominates telescope. Now, if this is sounding, let's say, trivial or obvious, notice that this sentence is ambiguous. It has two different structures. Okay, so VP dominates saw a boy with a telescope is okay. PP dominates with a telescope is also okay. But a boy with a telescope and a boy, so a boy is an NP. A boy is an NP. A boy with a telescope is also an NP. Okay, so we could have a noun phrase dominate a boy with a telescope, meaning thereby the boy has a telescope, or the domination could be distributed. NP dominating a boy, PP dominating with a telescope, and of course VP dominating saw a boy with a telescope. Now the ambiguity is in subdomination. VP dominates saw a boy with a telescope. So mark this carefully. VP dominates saw a boy with a telescope. So any ruler will have to rule through his assistants. In this case, the ruler VP, the dominator VP, has three assistants, V, NP, and PP, all at the same level. Okay, so the commander has three sub-commanders, all at the same level. And therefore, we have V, NP, and PP distributing themselves, their dominations over these three segments, saw, a boy, and with a telescope, giving rise to the meaning that I have the telescope. The other domination is, no, there is no picture there. So other domination, in the other case of other domination, VP has two assistants, V and NP. The next NP, the NP dominates a much bigger chunk. The whole sequence of a boy with a telescope. Okay, and that will produce the meaning that the boy has the telescope. So the phenomenon is domination, that is language science. Modeling of domination through probability is the data science. Okay, now let's see how domination gets modeled through the instrument of probability. Okay, so we need data for all this. Probabilistic parsing, machine learning based parsing, we need data. But before that, let us do something more. Let's talk about the domination a little bit more. So we have to understand the notion of probability of a parse tree. The probability of a parse tree is defined through the linguistic phenomenon of domination. We say the non-terminal Nj dominates from between word indices k to L, symbolized as Njkl, if Wkl is derived from Nj. Okay, so the probability of the whole parse tree given the sentence is equal to probability of the tree given S0 to L. S0 to L is the between word indices going from 0 to L, covering the whole sentence. Where S0 to L means that the start symbol S dominates the word sequence, W0 to L. And PT given S approximately equals the joint probability of constituent non-terminals dominating the sentence fragments. Okay, let us see what I mean by that. We have the index sentence, the gunman sprayed the building with bullets. The indices are given here, 0, 1, 2, 3, up to 8, where 8 is after the full stop. Okay, so we have to compute the probability of the parsing. We have S as the starting symbol, the root of the tree. S is between 0 and 7. S dominates 0 to 7. NP dominates 0 to 2. That is the gunman. VP dominates the building with bullets. And all the indices are recorded along with the symbol. Okay, when I say PP 5 to 7, that means a preposition phrase dominates from 5 to 7, that is with bullets. Okay? Or a PP yields, the yield of PP is with bullets. Okay? So probability of the parsing given the sentence is defined this way. It is defined this way. Probability of T given as 0 to 7. Now, S0 to 7, the meaning of S0 to 7 is S dominates 0 to 7. That is from beginning to end of the sentence. Here comes the probability and the phenomenon. We say the probability of domination by S is the joint probability of NP02. That means a noun phrase dominating 0 to 2. DT dominating 0 to 1. And then seeing a the. Okay, then W01 dominating 0 to 1, which is the. NN dominating 1 to 2, and W1 to dominating gunman. So what is happening here? So look at this. S dominates 0 to 7. NP dominates 0 to 2. DT dominates 0 to 1. That dominates W01. Okay. So we this way we keep recording the domination by symbol, and we say that this domination is the joint probability of all these small domination. Okay, and this is not different from asking the following question: what is the probability of getting a head and an even number when we toss a coin and a dice simultaneously? What is the probability of the whole sentence, the S symbol dominating the whole sentence? That probability is a joint probability of various non-terminal symbols dominating parts of the sentence. Okay, so this is a joint probability, and now we'll have to break this joint probability into its components. The first step, of course, will be chain rule of probability. And then there will be independence assumption. So let's do that after the break for 2-3 minutes. Give your attendance sheets to Manishit and Kishan. So probabilistic parsing is one of the most interesting topics in NLP. And it became possible when data arrived. Before data, people had a notion of doing parsing through some kind of decision-making process, which can be trained on a model. They had a notion. But all these were going nowhere because there was no data. What is the data? What data do we need? Now, probabilistic parsing, it requires probabilities. The probability of the tree needs to be computed. The probability of the tree needs to be defined before that. The probability of the tree is defined by means of domination. There is the probability of subtrees, and probability of subtrees ultimately boils down to probability of a pause tagger for a word, and also the probability of a larger constituent being composed from smaller constituents. Okay, the noun phrase is composed from NPPP, or noun phrase is composed from determiner and a big noun phrase. Okay, those are the questions, and that is the uncertainty. So let's begin. Let's first ask what kind of data we need for probabilistic parsing. So the parse tree looks like this. We know that S goes to NPVP, and then V NPPP, and so on. And if it is a dependency parse tree, then we have the main verb, and then there are arguments linking with the main verb through different levels. So the data is called bracketed structure. Okay. So if we have this sentence, I saw the boy with the telescope, and I have the telescope, then the parse tree can be depicted as this diagram. This means I have the telescope, or it can be depicted by a linear structure like this. What is a linear structure? I have S. Okay, look at the outermost bracket. It is S. Then the outermost bracket has lots of sub-bracketed entities. So I have the first bracketed entity as I, which is an NP. And then I have a fairly large bracketed structure. I think I should use this. So I have this bracket and the closing bracket here, which is VP bracket. This means I have a word phrase here. The word phrase, which is a bracketed structure, has smaller bracketed structures. This is a bracketed structure which is saw. That is within two brackets with VBD as the label. And then I have a bracketed structure here, the boy, which is an NP. Of course, the boy, which is an NP, has sub-bracketed structures within itself. Okay, when you go to the lowermost level, the words themselves are bracketed structures. And then with a telescope is a PP structure. So just think a little bit and see that this whole thing, it can be written as a linear sequence. You see that? Okay, so that is the that is a machine learning problem. That parsing is also a sequence leveling problem. This is the input sequence. And I run another sequence which is parsed. So we'll wonder, tree is a two-dimensional structure. How can I have a linear sequence which is a parsed tree? We can have. So first of all, I'll put a bracket here. Now I am the sequence leveler. I'm the sequence leveler. I put a bracket here, and I put a bracket here with S as the lower suffix. Then I put a bracket here, and I put an entry here. So I'm the sequence leveler. So the boy with the telescope I know is a VP. So notice that all I'm doing is labeling a sequence. And the output is also sequence. The only difference between the input and output is that the output is embellished. Okay, embellished with brackets. If I drop the labels here, then I have an unlabeled bracketed structure, which is easier to construct. So is VBD. This is also linear sequence. I put a opening bracket, next part of the sequence, closing bracket, then underscore VBD. Everything is sequence level. The boy, I decide that I open a bracket here. Now, where should the closing bracket be? That's the decision problem. And I have acquired the ability to answer this decision problem because of learning. I have learned. Okay. The boy, should I place the bracket here? Or I'll place the bracket going up to telescope and put a bracket there. If I take this bracket right to the end, telescope, then I'm saying that there is a large noun phrase, the boy with a telescope, and the boy has the telescope. And if I don't do that, then I place a bracket here and finish the story that there is a noun phrase here with NP. With a telescope, I know I'm starting with, so there must be a preposition phrase. Here the decision problem is easy because at this position, I have got a features. I've got a very strong signal. Okay, which level should be which level is starting to form? The level that is starting to form is PP because the signal is very strong. It is with. There is no other possibility. A phrase which starts with has to be a preposition phrase. Can it be a verb phrase? No, because with is not a verb. Can it be a noun phrase? No, with is not a noun. But if it was starting with above, if it started with above, would you be certain? You will need more signal. Above can be a noun. Above can be an adjective. Above can be a preposition. So I'm not certain. But with is a preposition. Okay. So here there is no ambiguity. My decision making is easy because of this very strong signal. If this was above, I'll have to do more work. I'll have to take more context. I'll have to look ahead. I'll have to collect more features. I'll have to do feature aggregation through a neural network or a conditional random field, which you're doing for part of speech tagging. Okay. So you see, how can you avoid probability in NLP? You just cannot avoid. You cannot avoid. Everything is ambiguous. Words are ambiguous, phrases are ambiguous, their connection is ambiguous. Where should I start an entity? Where should I end it? Ambiguous. Okay, so we need strong grounding on probability to to design strategies to solve language processing problems. So with is a preposition. With a telescope, we'll end here with a PP, and with must end. With must be bracketed by a P. A telescope will become noun phrase. Now see that I've done only sequence labeling, inserting opening brackets, closing brackets, and labels. And I'm doing it for every position. Okay, so between so just before the first word at the 0th position, at the 0th index, I'll have to have two brackets. And then at 1th position, I'll have to have a closing bracket and an opening bracket. Okay, and then I'll have to have an opening bracket again. Then the next word saw, and after this again one closing bracket and an opening bracket. All these I have learned. Okay, all these I as a machine have learned. Or as a human being, I have learned the grammar, and the properties of words and their interaction. So in producing this sequence level, I am making use of my knowledge of English language and its grammar. If it is a machine, it will have to be given this kind of data that you see. And now this is not there's nothing but a sequence leveling problem. Input sequence, output sequence. And we have many machines for doing this. We have encoder, decoder, we have transformer, we have rules, we have support vector machines, we have conditional random fields, so many machine learning algorithms for this. But the point is that at every stage, I'm making decisions. Any question? Yeah. No, not any number. Decided by the graph. Some phrases, yeah. Good question. Can we even learn? Yeah, can we even learn? There are very successful probabilistic parsers. Okay, since 2001, very successful probabilistic parsers. Before that, parsing used to be a very specialized task. So Xerox was the company which was dominating this field. It had some 100,000, 200,000 rules for parsing. When this kind of parse structures data became available, the whole parsing business was democratized. Anybody with a machine learning model and the parse data can create a parser, just like what is happening now. Anybody with some data and access to transformer can create any NLP system. Okay, so what is the learning part here? The learning part, which is sometimes missed, is the fact that a parse tree is not a tree; it is a sequence. For our purpose, a parse tree is also a linear sequence, which is amazing. So any graph can be linearized, right? So even semantic graphs will be a sequence leveling problem. So if anything in NLP is mostly a sequence leveling problem, I therefore want a good sequence leveler. Unfortunately, we have these recurrent neural networks leading up to transformers and large language models. But the foundation is this. Any question, comment from anybody? Okay, so let's little more. Now you see the other parse tree. This parse tree says that the boy has a telescope. Now see the noun phrase here. The noun phrase is much bigger. It starts here and ends here. The boy with a telescope. The whole thing is a parse tree. Is a bracket structure, as opposed to this, where the boy is a separate structure with a telescope is another structure. Two smaller structures side by side. And in this case, the structure is much bigger with structures inside. Okay, now let's begin to become more rigorous on this. So first, we have to define what is called probabilistic context-free grammar, because we have data in the form of parse space. So probabilistic context-free grammar is exactly like context-free grammar. The first component of PCFG is WK, K going from 1 to V, where WK is the vocabulary, the words in the language. So child, teddy, bear, played, all these are WKs. Then a set of non-terminals, NI. So NI goes from I1 to N, where there are N non-terminals. NI, the set NI can have entities like NP. NP is the noun phrase, VP verb phrase, dt, the determiner, and so on. A designated start symbol S, sometimes given the symbol N1. Okay, so S is special, S is the start symbol. A set of rules, Ni going to zeta j, where zeta j is a sequence of terminals and non-terminals. For example, NP going to dt and n. So far it is context-free grammar. Okay, so far it is context-free grammar. A corresponding set of rule probabilities. So all the rules will have a probability value associated with them. Here is the example. The rule probability is such that for the same non-terminal, all production rules sum to 1. So the probability of NP going to DT and N is 0.2. Probability of NP going to NNS is 0.5. Probability of NP going to NPPP is 0.3. See that the sum is 1. So what is the meaning? The meaning is that 20% of the training data parses use the rule NP goes to DTNA. Okay, so 20% of the noun phrases are determiner followed by noun. This you can easily obtain by counting and taking the ratio of counts from the annotated data. Now comes a very important question. What is the meaning of probability of NP, arrow, DT, NN? What is this entity? NP goes to DT, NN. Linguistically, I know. NP going to DT, NN is a linguistic phenomenon which says noun phrase consists of determiner and noun. But probability does not understand that language. Probability says probability of a random variable. So inside the P, NP goes to DTNN, I would want a random variable. What is this random variable? And random variable stands for a phenomenon. What is the phenomenon? Okay, so what could be the answer? What is the phenomenon? What is the random variable here? Hmm? Roles for a given POS time. Take the third one, probability of NP going to NPPP. Please. Have you seen any probability expression where there is an arrow? No. Probability is always expressed through random variable. This is a conditional probability. Probability of the right hand side given the left hand side. The random variables are NP, PP, and NP. Okay. Now it is still not clear really. Okay, it's not clear because the random variables NP, PP, and these are joint probability. NP and PP is a joint probability coming together. And this bar indicates a conditional probability. So this is a joint probability, this is a conditional probability. Conditional probability of what? What is that? Can anybody tell me? So the phenomenon is splitting into. Little more technical. This is compiler language, programming language. That's same as what we say, splitting into. Okay. So no, we'll bring the correct language. What is the probability that a noun phrase dominates another noun phrase followed by a preposition phrase? Because a noun phrase could have dominated a determiner and a noun. Okay. Amongst all the possibilities of obtaining a noun phrase, constituting a noun phrase, which is domination. So this let me write here. That is the meaning. Dominate. Hmm. Yeah, always. But in real life, of course, up to a certain age. But here always. Okay. So the meaning. So this is really very beautiful. The meaning of arrow is conditional probability, and the meaning of the right hand side is a joint probability. That is the meaning. Okay. If that is the meaning, now you apply chain rule of probability, Markov independence assumption, and see how the probability is computed. But before that, we need a few assumptions, independence assumptions. The assumptions in the PCFG model. First assumption is place invariance. It is also called stationarity. The probability of NP goes to DTNN is the same independent of the location in the tree. Okay. So the probability of the noun, probability of the probability of pos tag noun following an adjective JJ is independent of the location of this adjective noun combination. This is the place invariance or stationarity assumption. So think of where this assumption would be wrong. This looks like a very intuitive rule and probably obvious also. Okay, the probability of NP being expanded as determiner and noun is independent of where that phrase appears in the sentence. Okay, but think of, is it true really? In the world of language, is it true? Okay, think of that. The next two assumptions are the heart of computation. The context freeness assumption. The probability of NP going to DTNN given the siblings of NP, okay, is equal to probability of NP going to DTNN. That means the siblings have no influence on that probability. This is the context freeness assumption. It is independent of the context. And the next assumption is ancestor freeness assumption. Probability of NP going to DTNN given all its ancestors up to the root is equal to probability of NP going to DTNN. Okay, so this means whatever with the ancestor, the probability of the rule is independent of the ancestor. This is called the ancestor freeness assumption. Quite intuitive and looks reasonable. Assumptions look reasonable. Your task is to find out what is the what is the shape of these assumptions in post time? The context freeness and ancestor freeness assumption translates to n-gram assumption. Bigram, trigram, okay? This essentially mean n-gram assumption. Okay, so if we have these assumptions, context freeness and ancestor freeness, then the computation of the probability of a tree is quite possible now. So the probability of the whole parse tree is nothing but the probability of the all the non-terminals and terminals appearing jointly. So now begin to see the application of this independence assumption. So this whole probability of I can break this probability into probability of NP VP given S, first of all. The NP is from 0 to 2, VP is from 2 to 7, multiplied by the rest of the joint probability expression. Probability of DT, NN, and everything else given S and the first part of the chain rule. So this NP02 and VP27 will now go into the conditioning part, right? So we'll have probability of DT NN given NP02, VP27, and S02. So now this will become equal to probability of DT NN given NP02. VP will get dropped because of context freeness assumption. Siblings have no effect. And S07 will get dropped because of ancestor freeness assumption. Because ancestors don't have any influence. Okay, then effectively what will happen is that the whole of computation will boil down to taking the product of the probabilities of all these rules. Okay, so S goes to NPVP is 1, NP goes to DTNN is 0.2, DT going to the is 1, only 1, NN going to gunman is 0.5, and all these probabilities will be multiplied and the probability of the tree will be computed. If there are multiple parse trees, then the probabilities of all the parse trees will be computed, and the parse tree whose probability is highest will be the winner parse tree. Exactly like the post stack sequence whose probability is the highest will be the winner post stack. The hidden Markov model is computing the highest probability post stack sequence. So here, the probabilistic context tree grammar will compute the probability of the highest probability parse tree. There is a Viterbi-like algorithm here also, because if there are multiple parse trees and you have to compute the probability of all the parse trees, then you can have inefficiency, and you should be using the partial work done. That is, dynamic programming should be used. Now you might come back and ask, why should I worry about efficiency? In post stack sequence, I understand. At every position, 40 post stacks are possible. Okay, so 10 to the power 40, I'll have to search amongst these possibilities. Here, why should I worry about any kind of inefficiency? A sentence can have at most 2-3 parse trees. If you think so, then you will be deceived, because the number of parse trees given a sentence can be exponential in the worst case. It is governed by a concept called Catalan number. Catalan number. Okay, the number of parse trees of a sentence can be shown to be almost equal to Catalan number for n, where n is the length of the sentence, and that is an exponential quantity. We'll talk more about it later. So one or two announcements. On Saturday, I think at 11, 11 or 11:30, I don't remember now. 11, I suppose. We have the assignment presentations and demos. So you are given a template of slides which you should fill and only show those slides. Okay, no extra description, exactly what is asked for in the slides. That is because we operate with time constraint. The class size is big. And the second is that all the members of the team should be present. This is an online demo, so all of you should be present. Okay. And we'd also like to ask you who has taken how much of the task on himself or herself. That is one. Second is that all the evaluation team members, each team consists of 2 TAs. Only one team has 3 members. That is me and 2 others. So for each evaluation team, a set of groups have been assigned. So all these evaluation teams have their office hours. I also have my office hour. I'll announce all these office hours will be announced on the Teams channel. So the evaluation team should be present in C field at the appointed office hour. So if my office hour is, let's say, 2 to 3 o'clock on Friday, every week 1 office hour, then I will be found in my office, which is 510 in the new CSC building. At that time, you can come and discuss your doubts. Similarly, for every team of TAs, there will be an office hour. Go and talk to them about your doubts. Okay, so office hours announcements. Now, I wanted to discuss the remaining 2 questions in quiz 1. I'll do it at some point of time. But please convince yourself that left to right pause tagging and right to left pause tagging has no difference. It doesn't matter which direction the scanning is. Okay.